The first one is sort of a more general quantum gravity announcement. We just like to advertise that Aaron Held and some colleagues are organizing the fourth mini workshop on quantum gravity in January, which may be of interest to this audience. And Aaron, I think, should have just shared or will soon share a link in the chat for anyone who's interested. And then for, I guess, logistics, Daniel has said that he's happy to take questions during the talk. So we'll proceed more or less as we did the past couple of talks. If anyone has questions during the talk, maybe post them in the chat and I'll interrupt Daniel at an opportune moment. We can mostly go for sort of clarification questions, but Daniel is also happy to have some more discussion-based questions during the talk. But any much longer sort of discussions we'll save for the Q&A afterwards. Okay, with that out of the way, let me introduce our third speaker, Dan Harlow. Just to give you some background for those who may not be familiar with him, he got his PhD at Stanford in 2012, after which he did 2 postdocs, one at the PCTS at Princeton, then at Harvard. And then in 2017, he started a faculty position at MIT, where he is currently. He's made many very important contributions to ADS-CFT and quantum gravity, so things like the black hole information problem, firewalls. Recently, he's done some interesting work on global symmetries, which we may hear about in this talk. And he's also worked on sort of interesting connections between quantum gravity and quantum information, specifically in the context of ADS-CFT. So things like quantum error correction and bulk reconstruction in that context. For that work, he was awarded the 2019 New Horizons Prize in Physics for fundamental insights about quantum information, quantum field theory, and quantum gravity. And I think just 2 months ago, he was named a Packard Fellow for Science and Engineering. So we're very happy to have Daniel here to talk to us about global symmetry, quantum error correction, and the black hole information problem. So take it away, Daniel.
Hi, everyone. So thanks for the invitation. I changed the title from what was announced to try to fit it in a little bit more with the theme of this, what's been going on in the talk so far. So instead of talking about Euclidean gravity, I'll say a bit more about quantum error correction. Let me see, here we go. Okay. So the main theme of the talk today is going to be about this idea that in quantum gravity, there are no global symmetries, which is an old idea. Actually, it's older than the references that I have here. These are the papers where I could find explicit statement of this, but my understanding is that the idea that quantum gravity shouldn't have global symmetries goes back, say, to Zeldovich on one side of the Iron Curtain and Wheeler on the other side. Although I so far haven't managed to find specific references. If someone knows older papers, I'm happy to hear about them. The basic idea is that, well, the reason why you can't have global symmetry is because you can take a charge, something which is charged under global symmetry, and throw it into a black hole, and somehow that destroys the charge. Now, this argument by itself is not very good, because you can just say, well, why didn't the black hole carry the global charge? Okay, and instead of just saying it was destroyed. So you need to say a bit more to say why somehow the black hole can't carry the global charge. So in the case where the symmetry is continuous, there's an argument which again goes back further, but I think was first written down in this paper of Banks and Seiberg, where basically you argue that since if the global symmetry group is continuous, like say it's U1, then the total charge can be unbounded, and that's basically an infinite amount of information. And if we think that black holes only have a finite entropy for a black hole of finite size, then such a black hole cannot store an infinite amount of information. Now you could worry that, okay, fine, but maybe you just can't prepare a black hole of a fixed mass with an arbitrarily large charge. But actually you can argue that you can, because you just, you take a black hole of whatever mass, you throw in as much charge as you want, and then you let it evaporate back down to the mass that you started with. And since the Hawking process doesn't produce plus or minus charges preferentially, you'll end up with the black hole of whatever mass you wanted with the charge as large as you like. At least if you believe in the Bekenstein-Hawking formula, then you probably shouldn't believe in continuous global symmetries. Okay. for the case of discrete global symmetries, that argument doesn't really work because then the charge is not unbounded, right? Like if it's a Z2 global symmetry, the charge is plus or minus 1, that's it. So there's not going to be any tension with the Bekenstein-Hawking formula. But by using ADS-CFT, which I'll talk about more in this talk, you can give sort of some version of this argument, which still excludes both continuous and discrete symmetries, so all global symmetries. On the other hand, ADS-CFT is clearly too strong of an assumption if we really think that this idea that there are no global symmetries in quantum gravity is robust, right? I mean, in particular, we might like it to apply to our world. And as far as we know, the cosmological constant in our world is not negative. So, we need to back off, this use of ADS-CFT. Even though I did it, I at the time I knew it was too strong. Okay. On the other hand, there clearly has to be some kind of assumption, as we'll see in this talk, because in sufficiently low dimension, there are theories of quantum gravity with global symmetries, and we'll give some examples. So, so there needs to be some kind of non-trivial assumption that excludes them. So in this argument described by Banks and Seiberg, the assumption was that the Bekenstein-Hawking formula is correct. We want some kind of assumption like that, okay, but that's good enough to also rule out discrete global symmetries. So the main goal of this talk, although not the only thing I'll explain, is to propose what I view as a kind of plausible, sufficient condition for excluding global symmetries in quantum gravity. And so this is based on a paper with Edgar Shaghoulian, which came out a couple weeks ago, so fairly recent paper. Here's the proposal. The proposal is that in any theory of quantum gravity where black hole evaporation is a unitary process, and moreover that is consistent with the Bekenstein-Hawking entropy formula, or more generally the Wald formula, then no global symmetries are possible. So this is the same kind of input that went into the Banks and Seiberg argument, but we're going to see that we're going to be able to rule out discrete global symmetries as well. And maybe also we can say give a different perspective on why continuous ones are not allowed. On the other hand, we had to assume a bit more. Instead of just assuming the Bekenstein-Hawking formula, we also had to assume something about the evaporation process. Okay. So, you assume a bit more, you get a bit more. Now, I'm not going to prove this in this talk. We don't know enough about quantum gravity to prove things like this, right? I mean, this is some statement about all theories of quantum gravity, and we don't. Well, the theories of quantum gravity we have are quite few, and none of them are realistic. So, so we're not in a position of proving this at a level that would satisfy a mathematician, or even a physicist, really. But on the other hand, I will give some evidence for this proposal. And the evidence is going to come in two kinds. So the first kind will be that I'll show that in these examples I mentioned of quantum gravity theories with global symmetry, this assumption is not true. Okay. So that's at least one obvious check of this proposal, right? I mean, had it been true in those examples, then clearly this proposal would be wrong. Okay, so that's some natural set of counterexamples one could check and exclude. Probably a stronger argument, though, will be that I'll show that my argument with Hirose from a couple of years ago can actually also be applied to exclude global symmetries more generally in any theory of quantum gravity where the recent calculations of the Page curve, which were explained by Pennington, Almeri, Engelhardt, Mouth, and Maxfeld last year, are valid. So I'll say a bit more about these calculations later. Hopefully you heard about them before. If you haven't, then you should go learn about them. This second argument, basically what it does is it reduces this proposal to the statement that this scenario explained in these papers is the only way for black hole evaporation to be unitary and compatible with the Bekenstein-Hawking formula. And this is, of course, not something I can prove. I can't it's certainly not now. I mean, maybe at some point in the future we'll understand quantum gravity better, but right now I'm not in a position to say that this is the only way that things can work. On the other hand, this is a very general mechanism. It basically, it uses sort of only general features of holography, and it gives you the right answer in a very nice and plausible way. So I don't think it's crazy to think that this is how things always work. But anyways, for this talk, that'll just be an assumption. And that's why I say that I'm giving evidence for this proposal instead of proving it. So that's it for the introduction. Any questions, concerns, comments about the introduction? Otherwise, we'll get into it.
I see no questions right now.
Okay. Well, in that case, okay. So I want to then start by talking about these low dimensional theories that do have global symmetry. So if we're gonna try to exclude global symmetries, we have to first understand, these examples. What are these examples missing that somehow is essential for arguing that there's no global symmetries? So the first two examples I'll discuss are pretty stupid, but I want to. Oh, now there's a question from Deepak.
Hi, Daniel. I guess my question is pretty naive. It's why are global symmetries bad?
I guess that's what I'm going to try to explain. I mean, but very roughly. So maybe let me rephrase your question. So what is it that's bad about global symmetries that's not bad about gauge symmetries? Are you happy with that version of the question?
Okay, sure.
Yeah. So the key difference is that for a gauge symmetry, if you want to know how much charge there is in a region, you just have to make a measurement at the boundary of the region. So that's what I teach my students in my first year electromagnetism class, and we call it Gauss's law for the case of the U1 gauge field. Whereas if you want to know how much global charge there is in a region of space, the only way to find out is just to go look everywhere and add it all up, do a census. And in holography, the microscopic description of everything lives at the asymptotic boundary. So somehow that's more natural from the point of view of gauge symmetries than it is from the point of view of global symmetries. Somehow, now, on the other hand, well, we'll get into it, but I mean, for global symmetry, I mean, there are operators far from the boundary, which makes sense, even in holographic theories. But a symmetry operator turns out to be too simple to be able to reach into the bulk. Whereas for gauge symmetries, it doesn't need to reach into the bulk. It just needs to detect the gauge field at infinity. So hopefully that's enough to be getting on with, and maybe it'll be more clear as we go on.
Well, would it be fair to say that you can't have global symmetries because of the requirement of diffeomorphism invariance?
No, that's definitely not fair because well, for one thing, these low dimensional theories I present are going to be diff invariant, but they're still going to have global symmetries.
Okay. All right. Thanks.
It looks like Prahar has a question.
Hey, Daniel. So would your comment also apply to these asymptotic symmetries that Andy and company have been, like the local ones, which, in principle can be measured locally?
Those are not global symmetries, right? Those are gauge symmetries.
They're gauge symmetries, but they're physical symmetries, right? That there's physical charges that act.
Yes. So there's a confusion about. So okay, I wasn't going to talk about gauge symmetry in this talk, but some gauge symmetries are physical.
Okay.
So
okay. That's fine.
And for example, just in ADS CFT, right? We often, in Ed's paper, it says that a global symmetry in the dual CFT is dual to a gauge symmetry in the bulk. Okay. Now, clearly, whatever a global symmetry is dual to, it's not just going to be a redundancy of description.
Yeah.
Okay. So in my paper with Hiroshi, we discussed that at great length, and we introduced something we call long-range gauge symmetry, which is the physical part of the gauge group. And that's that's right. So in these asymptotic symmetries are like that.
So here, would you say that you're calling global symmetry as anything that would require you to be a non-local observer, like to be able to measure?
Well, a global symmetry, the definition of a global symmetry is it's a symmetry where there are local operators that are charged under the symmetry. In quantum field theory, that's the definition. In gravity, you have to be a little bit more careful because of diffeomorphism dressing.
Mm-hmm.
But essentially then what you have to say is there are endpoints of gravitational Wilson lines that are charged under the symmetry. And that's not true for these asymptotic symmetries.
Yes.
If for the asymptotic symmetries, it's the Wilson lines that are charged. That's the key difference, is these asymptotic symmetries it's line operators that are charged under them, not local operators.
Yes. Okay. Thank you.
Okay. So let's move on. So let's first think about these simple low-dimensional examples. So I'm going to start with some trivial examples. So these are about as trivial as you can get. So the first one will be 0 + 1 dimensional. It's just the theory of the world line theory of a relativistic particle. So the action is just the proper time along the world line. So that maybe doesn't look like a gravitational theory, but you can integrate in a 0 + 1 dimensional metric, GTT. And then if you look at this action, right, it just looks like you've got some matter fields, x mu, which are interacting with the 0 + 1 dimensional metric, GTT. So this is a diffeomorphism invariant action, commenting on the previous comment. And it's it has a dynamical metric. Okay. Similarly, in 1 + 1 dimensions, you can have the Nambu-Goto action, which is the area of the world sheet, which you can again introduce a 1 + 1 dimensional dynamical metric G. So this is called the Polyakov action. And you see again, we have matter fields x mu coupled to a dynamical metric G with full diffeomorphism invariance, right? But both of these have a global symmetry, which is the Poincare symmetry of the target space. So these matter fields x mu, there's some symmetry that rotates them and also with an additive shift. And this is just the global symmetry of these theories. Okay. And these theories are exactly soluble. The symmetry is preserved in the quantization. So it's really an exact global symmetry. Now, the reason these examples are silly is because they don't have black holes. So since the arguments that there aren't global symmetries somehow involve black holes, you wouldn't maybe really expect them to apply to these theories. But still, I think they're important because they show that just having a dynamical metric and diff invariance isn't enough to exclude the presence of global symmetries, right? Now, okay, those examples were kind of silly. Let's talk about a less silly example. So this will be the ADS version of Jakiv-Teitelbaum gravity coupled to conformal matter. So this is a 1 + 1 dimensional theory. So let's go through it. So there's three kinds of dynamical fields. There's a scalar field phi, which is called the dilaton. It's kind of a bad name, but that's what it's called. There's a metric G mu nu, a 2-dimensional metric, which is dynamical. And then there are matter fields psi, which are the matter fields of some 2-dimensional conformal field theory, which we take to be minimally coupled to the dynamical metric. Okay, so this is kind of like an Einstein term. This is kind of the kinetic term for the matter fields. And then it also has this funny extra feature that you can add a topological term to the action. So this phi naught is not a dynamical field, it's a parameter. So, and it multiplies, oh, well, I made a typo. It should be multiplying the Ricci scalar here, my apologies. So it should be phi naught times R here, which is kind of the, then by the Gauss-Bonnet theorem is topological. And then this here is kind of the boundary term for the Gauss-Bonnet theorem. So what this phi naught basically gives you is it gives you a contribution to the action, which is 4 pi phi naught times the Euler character of the space-time. So this is just a parameter in the theory. You can always add to the action a multiple of the Euler character and write that as a local integral made out of the metric. Okay, so this is some 1 + 1 dimensional theory of gravity coupled to matter fields. And again, it's fully diffeomorphism invariant, has a dynamical metric. So at least on the surface, it's a theory of quantum gravity. Now, moreover, it's a renormalizable theory of quantum gravity. And after canonical quantization, you can exactly solve it by a Weyl transformation to flat space. So that's some 2D methods that I won't go through in detail. When I say exactly solve, of course, this matter CFT might be strongly coupled. It might be some fancy irrational 2-dimensional CFT. So when I say solve, I don't mean you can solve the CFT. We can't solve all 2-dimensional CFTs. What I mean is that the observables of this gravitational theory can all be expressed in terms of the flat space correlators of this CFT, which we may or may not know. If we take it to be a free theory, then we know them. But if we take it to be some strongly interacting theory, then we don't. Now, the key point is that this matter CFT can basically be whatever we want. The only requirement is that it shouldn't have any diffeomorphism anomalies, which means that its left and right central charges need to be equal. If you don't know what that means, don't worry about it. So in particular, this CFT can have a global symmetry because it's just some two-dimensional conformal field theory, and there are lots of two-dimensional conformal field theories with global symmetries. For example, we could just take this to be n free Dirac fermions, and then there's a UN flavor symmetry rotating them into each other, which is a global symmetry. And this global symmetry survives the canonical quantization of this theory and becomes an exact global symmetry of the quantum theory. So this theory, again, has a global symmetry. Now, this theory is a little more interesting than the previous two examples, and the reason is that at least in some sense, it does have black hole solutions. I'll, in a little bit, maybe 20 minutes or so, I'll talk about what those solutions look like. But let me just comment now that we'll see, though, that although it has solutions that are black hole-like, their entropy is actually infinite. It's not given by what the Bekenstein-Hawking, the analog of the Bekenstein-Hawking formula would say in this series. And so these black holes should really be thought of as remnants in some sense. So this theory is unitary because we just constructed from canonical quantization. You can arrange for the black holes to evaporate, as we'll discuss. But the evaporation doesn't have a page curve that goes up and then goes down. It just goes up, 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 and leaves behind a remnant, which is, one of the three options for the black hole information problem. And in fact, if you're old enough, you remember there's this thing called the CGHS or RST model. And this basically works in the same way as that. So that also has the unitary evaporation that leaves behind remnants. So in any theory with remnants, the Bekenstein-Hawking formula is not going to be correct. And that's true in this theory. So therefore, this theory does have unitary evaporation, but it's not consistent with the Bekenstein-Hawking formula. So then our conjecture here allows it to have global symmetries. Which is good because it does have global symmetries, or at least it can if we take the matter CFT to have them. Okay, I want to give one more example just so that you think the action is an all in 1 + 1 and 0 + 1 dimensions. So we can also think about pure Einstein gravity in 2 + 1 dimensions, which I will take to have a negative cosmological constant. And I will also take to be oriented in the sense that we only include oriented spatial manifolds. So that when you quantize this theory, you have a choice. Do you allow unoriented spatial manifolds or not? And so we're going to not allow them. So you can try to quantize this theory in Euclidean signature, which is, I guess in this talk, I suppressed most of the talk about Euclidean gravity, but here I mentioned it once. But it's not so clear whether that makes sense, at least not without further input from the UV. But this theory is renormalizable. It can definitely be canonically quantized. And that was studied in these papers from 2015. In particular, in the oriented version, it has a global symmetry, which is parity. So there's a global symmetry of spatial reflections, which for the oriented case is a global symmetry. Had we, if we had allowed unoriented spatial topologies, then it would have been a gauge symmetry. So parity in oriented 2 + 1 gravity is also a global symmetry in a theory of gravity, now in 2 + 1 dimensions. So that's it for the examples. Any questions, concerns about these examples? Then if not, I'll go on and try to think about what these examples are missing.
I don't see anything.
Going once, going twice.
I just may have a question.
Okay.
Is this at all related or obviously related to the Hilbert space factorization problem of JD gravity and pure 2 + 1 dimensional gravity? And how can I see if there is a relation between the absence of global symmetries and the fact that the Hilbert space is not factorized?
I think there's certainly some correlation with those issues. So it's true that if you just canonically quantize JT, the Hilbert space doesn't factorize. And so if you were hoping to get something holographic, then you're going to be disappointed. And that was one of the points of a paper I wrote with Daniel Jeffress a few years ago. You could just say, okay, well, too bad for holography, but this theory is fine. It makes sense by itself. And that's kind of the attitude which I'm currently taking in this section of the talk.
Okay.
If you want it to factorize, then you have to add additional degrees of freedom, which will destroy the renormalizability. So, so there's kind of a question of whether or not you view it as a low energy effective theory emerging from something holographic, or you view it as a world in and of itself. And so basically these examples with global symmetries are always going to be ones where you just view the bulk path integral as a self-contained thing, and you don't try to imagine anything fancy is going on in the UV. And that's kind of, I'm about to say this, but that's kind of related to why this only happens in low dimension, is because then there things are renormalizable and we can kind of get away with that.
Yes. Okay. Okay. Well, thank you. Thank you.
Yeah. Okay. So oh yeah, and I should mention that this theory does have black hole solutions, just like JT, but they again have infinite entropy. So our proposal allows for this global symmetry. So here the infinite entropy comes from two things. So basically the black holes here look like you have some handles or something behind a horizon. So some topological black holes. And then the problem is you can just have infinite numbers of handles back there, and moreover they're moduli, which when you quantize them lead to a continuous spectrum. So for both of those reasons, the black holes in this theory have infinite entropy. They do not have an entropy given by S equals A over 4G. And so therefore they're allowed to have global symmetries. It's allowed to have a global symmetry, and it does. Okay. So now let me kind of try to pivot a bit away from these theories and say a bit why I don't find them as a particularly good model of how I think things should work in higher dimensions. That's the obvious question is, okay, look, so you have these theories, so then why are you telling me this stupid thing that there are no global symmetries? You just gave me 3 examples or 4 examples where there's global symmetry, right? So, okay, so what am I doing, right? So let me first say that what I already said, which was that the fact that I could unambiguously quantize these theories and decide whether or not they have a global symmetry, decisively, is because they were renormalizable. So I didn't have to have a UV completion. And this is certainly not a property of Einstein gravity in 3+1 dimensions. Okay, so life is, certainly at a minimum, probably we're all going to agree life is not going to be so simple in 3+1 dimensions. Now, nonetheless, you can hope, and maybe some audience members do, that you could have some kind of UV fixed point of Einstein gravity in 3+1 dimensions. So this is sometimes called asymptotic safety. Although if I understand correctly, I think people who like loop quantum gravity also kind of are hoping for this. So my expectation, although I can't say that it's something that I know for sure, is that if this program makes sense, then it will allow for global symmetries and it will violate the Bekenstein-Hawking formula. And maybe part of my reason for expecting that is that I think of asymptotic safety as basically being analogous to what happened in lower dimensions, where the theory, you could just have a bulk path integral and you could do it. And the only difference is that there might be some other fields up in the UV, but you still, I think, if you believe in asymptotic safety, think the metric is one of those fields. And so then it should just kind of be a strongly coupled version of what we saw in lower dimensions. And since in lower dimensions, global symmetries were allowed and we violated the Bekenstein-Hawking entropy, then my guess is if asymptotic safety makes sense, then that's how it's going to work also. I should say so far, and maybe I don't know how controversial it is for me to say it, but from my point of view, I don't think there's at least convincing evidence for a fixed point like this in 3+1 dimensions. There's various arguments one way or the other, but I wouldn't say I saw anything that made me feel it's likely that such a fixed point exists. I also want to make kind of a moral comment, and so this maybe is more controversial, but I'm going to say it anyways. So if this were how gravity actually worked, then I think the apparent successes of black hole thermodynamics would be a mirage. because basically because I think in such a theory, remnants would be the answer to the information problem, and then it would just not be true that S equals A over 4G. So in the above examples, somehow the way that remnants sneak through in the 1+1 models is because even at zero energy, there are horizons. So there's a way to kind of construct the remnants and see how they work. And you also have this parameter phi naught that you can kind of use to hide the infinity, which you don't have in higher dimensions. And also in 2+1, these black holes in 2+1 gravity, well, at least in the cases where it's renormalizable, there aren't any quanta into which the black hole can radiate. So it's not so clear what the temperature means. So the failure of black hole thermodynamics in those examples is kind of less of a failure because it has these kind of unrealistic features. But in 3+1 dimensions, I think it would essentially just be, it would turn black hole thermodynamics into a conspiracy. The fact that you seem to have a first law and a second law that's consistent with S equals A over 4G, even though actually S equals infinity. From my point of view, and again, maybe this is also controversial, but I'm going to say it, all known UV complete theories of quantum gravity in 3+1 dimensions that have actually been constructed come from string theory. And those that we understand non-perturbatively, so some corners of string theory we only understand perturbatively, but the parts that we understand non-perturbatively are holographic in the sense that their fundamental description lives in a lower number of space-time dimensions at some asymptotic boundary. So for most of the rest of this talk, I'm gonna focus on these kinds of theories and see what the kind of constraints you get from this idea that things are holographic. So I'm going to now switch to talking about ADS-CFT, but first I'm happy to hear if anyone wants to try to correct me of the error of my ways or whatever about any of these comments.
Hi, Daniel. Just a question about the last point. In what precise sense do you mean all non-UV complete theories of quantum gravity in 3+1 come from string theory?
Well, yeah, I guess maybe the best way to say it is to focus on theories which are well defined in the sense that in principle you could put it on a computer or something, and which also have the property that at low energies you have the Einstein-Hilbert action and gravitons scattering in the way that the Einstein-Hilbert action would predict. To me, those are kind of minimal requirements of any theory of quantum gravity, and that plus requiring that the theory is well defined. So for example, that scattering up to arbitrarily high energies is in principle computable, I guess is what I mean by UV complete.
So can I interpret you're saying all the other approaches, they have these problems, like either, right. So what do you say about the other approaches? What are their problems? I mean, we can discuss this later, but
for the other approaches, there's no algorithm for determining the high energy S matrix, that you could put on a computer, because gravity is non-renormalizable, and that shows up in all of the other approaches. So you have to try to do something at high energies to fix that and get a theory that is well defined, and I don't think it's happened. Right? I mean, people try, right? There are various, things that you can try to do, but I don't think it shouldn't be too controversial for me to say that none of them have been sort of clearly successful in the sense that there is actually a well-defined algorithm that we could in principle run and see what we get, that doesn't depend on lots of arbitrary choices.
I'm a student, I'm not, so I don't have.
Sorry, if I may interject, this is turning into like a more extended discussion, which I might suggest we save to the end of the talk. So Daniel,
all right.
Yes, I was going to say, I'd like to see a discussion after your talk by people
yeah.
approaches.
We actively scheduled extra time at the end of the talks for exactly these sorts of discussions. So
Thanks.
Maybe let's let Daniel move on.
Okay. So let me now say a bit about holography. So our best understood example of a holographic theory so far, of course, this ADS-CFT correspondence, which says that quantum gravity in asymptotically anti-de Sitter space is equivalent to conformal field theory on its asymptotic boundary. So hopefully everyone knows what anti-de Sitter space looks like. You know, you have this can where you have the spatial slices are like this Escher picture, and then time is going up. And the basic rules of how the correspondence works is that any state of quantum gravity in the bulk is in one-to-one correspondence with some state of this in the Hilbert space of this conformal field theory on the boundary, so here if the bulk here is 2 + 1 dimensional, so the boundary here is 1 + 1 dimensional. So the theory is a circle is space times time. So that's some conformal field theory. It has a Hilbert space on a circle. And there's a one-to-one map between the Hilbert spaces. Moreover, the various symmetries mash up between the two sides. So for example, the Hamiltonian on one side is the Hamiltonian on the other, or the angular momentum, or any gauge charges, or what have you. And then maybe the kind of key element of, it's called the dictionary between the two sides, is that if you take an observable in the bulk, say like, so since Will gave a talk last time, I'll say a gravitationally dressed local operator sitting at some point here, and then you kind of pull it back along its dressing to the boundary, then you get a local operator in the dual CFT at the point where you pulled it back to. So here, t is time going up, omega is like the angular directions on this circle, and r is the radial direction. So I'm taking a bulk operator, I'm pulling it out to the boundary by taking r goes to infinity with some rescaling, and then I end up with some local operator in the dual CFT. So that kind of tells you how the local properties of the two descriptions are related, or at least part of how they're related. So then if you think about what these rules mean, well, one thing that they mean, for example, is that perturbations of the vacuum over here, like little ripples going around on the Escher, are low energy states of the dual CFT, while large perturbations here, which essentially all correspond to black holes, say very large black holes, for example, sitting here, correspond to very excited sort of quasi-thermal states from the CFT point of view. And so this is kind of ADS-CFT 101. And well, the reason we like it is because, okay, quantum gravity in ADS, that sounds confusing, you know, it could be 3 + 1 dimensional, for example. Einstein-Hilbert action looks non-normalizable, you know, don't really know what's going on. But then here we just have some CFT, it's a no gravity, it's a well-defined theory, at least by the standards of physics. And so in principle, the bulk must be well-defined too. Now, one of the most basic things that you can wonder about is how, so this I told you how to think about the limit of observables in here as I pull them to the boundary. But you could wonder, well, what about the observables that live deeper in, right? What about the observables that aren't just right next to the boundary? You know, if you say the Hilbert spaces are isomorphic, then you must be able to understand those from the dual CFT point of view also, but how does that work? And at first, it kind of seems impossible that it could work, because if everything is made out of the local degrees of freedom at the boundary, and we've already decided that the local degrees of freedom at the boundary correspond to things in the bulk that are near the boundary, then how can there be anything in the interior which is independent of what's happening at the boundary, right? Like, I mean, you know, if the local operators are near the boundary, everything is made out of the local operators. So doesn't that mean everything is near the boundary? So in other words, how can a theory which has d space-time dimensions, like the dual CFT, ever be equivalent to a theory that has d + 1 spatial dimensions, right? It seems like the d + 1 theory just has far too many degrees of freedom because it has this additional radial direction where you can put things wherever you want in the radial direction, and it seems like they should all be independent of the boundary. So you can phrase this a little more mathematically like this. So you think about having an operator 5x at some point in the middle of the bulk, and then you have some Cauchy slice here of the boundary theory where every point on this Cauchy slice is space-like separated from 5x. So then naively, any local operator on this Cauchy slice, O of x, is space-like separated from phi of x in the radial direction, so they should commute, because that's what operators do that are space-like separated from each other. Right? But then that sounds pretty bad, because this argument shows that phi commutes with all the local operators on this time slice. And then in quantum field theory, it's actually kind of an axiom or a general feature of quantum field theory that if you commute with all the local operators on a time slice, then you have to commute with everything, and you just have to be the identity. So in other words, the set of all operators on the Hilbert space of a quantum field theory is generated by the local operators alone. So that seems to suggest that this operator phi has to be proportional to the identity. Which is not very satisfying, right? Like we could be this operator here, and we don't feel, at least I don't feel like I'm proportional to the identity. Now, I just should mention, since it was discussed in previous talks, that this paradox is a little bit complicated by the need for gravitational dressing, because this operator really needs to have a line attached to it that goes out to infinity. And so there'll be one point, at least on the boundary, where it doesn't commute with operators there. But that's not enough to save you from this, because then the axioms would just tell you this operator has to be a local operator at that point where the line ends. And it obviously isn't, right? I mean, like, for example, I can have an operator over here that doesn't commute with it. So, maybe I'll stop again and ask if there are any questions about this kind of basic idea CFT comments. All right. So now this problem, and this is a bit of an aside, but I just wanted to mention it because I think it's important. So this problem is closely related to one that people who work on quantum computers think about. So when you're making a quantum computer, the memory of your quantum computer is going to be built out of an array of small quantum systems, often arranged in a lattice. So like on the Google quantum computer, these dots will be these superconducting crosses. But then in other architectures, they might be something else, you know, atoms in a trap or something. But there's always some set of local systems. And then the thing you have to worry about is that errors come. Like, so here's your quantum hard drive, and oops, here's a photon that comes in and bangs into this piece, or here's a photon that comes in and bangs into that piece or that piece. And that's just gonna happen. Like, there's no way to avoid that. So if you want to build a quantum computer, then you need to store the information in a way that where just a photon banging into any one of these isn't going to destroy the information. But that's actually kind of what we just said, right? So what we want is we want the state to be stored in a way that it's independent of what happens to any particular of the pieces, right? Because the photon could come in and bang into any of the pieces. And then we have kind of the same contradiction, right? Like if the information doesn't depend on what's going on with any of the pieces, then like how can the information be there? Because the whole system is just made out of the pieces. So somehow that something has to give here. Well, or we just don't have quantum computers. I guess that could also be the way to deal with this. Fortunately, that's not the way to deal with this. So any quantum information person, I don't know if there are any here, but if there are, they would tell you that the way you solve this problem is by using quantum error correction. And what we've learned, over the last 5 or 6 years is that this is also what solves the first problem and tells us how the things in the middle of the bulk can appear to be independent of the things near the boundary, even though they aren't really. So in other words, just to use quantum information language, although I won't use it again, so don't worry if it sounds strange, we should think of the center of the bulk as being logical information of a quantum error correcting code, and the boundary CFT is the physical degrees of freedom that the memory is made out of. So I just would say a tiny bit more about that.
Let me briefly interrupt just to give you a 10-15 minute warning.
Yeah, okay. So the basic idea of any error correcting code, quantum or classical, is to store the information redundantly. So for example, classically, the obvious way to do quantum error correction is if I want to send you a message and I want to make sure you get it, I just send it 100 times. And that way, even if it gets messed up a few of the times, eventually you can compare the ones you do get and figure out what the message is I was trying to send you with high probability. Now, that doesn't work quantum mechanically because of the no cloning theorem. You can't make 100 copies of a quantum state. But there's an alternative that works very nicely, which is that you can encode the information non-locally in the entanglement between the physical degrees of freedom. So I could give a whole talk explaining that more and giving examples of what it means to encode something non-locally in the entanglement between degrees of freedom, but that would be a different talk. So here I'll just leave it as a statement that hopefully doesn't sound too crazy. Instead, I'll just mention that this redundancy has an avatar in ADS-CFT. So using simple methods in the bulk, you can show that, so this disk here is a spatial slice of the bulk. You can show that given any boundary subregion R, there is some bulk subregion CR, which I shaded red here, such that any operator phi and CR can be represented in the CFT as an operator with the support only in R. So in other words, this operator is somehow independent of everything over here because I can just represent it here in the CFT. So for example, here, this 5x, indeed, I can represent it in R, but this 5y over here, I can't because it's not in this red region, CR. So this leads to some funny little contradictions. For example, here I split the boundary into 3 regions, R1, R2, and R3. And this operator in the center, oh, I forgot to relabel the things here. So this should be, instead of A, B, and C, it should be R1, R2, R3, my apologies. So this operator in the center, right, it's not in this shaded region for the CR, for R1 or R2 or R3, but it is in the shaded region for the union of R1, R2, or R3. So, and this is kind of this funny feature, is that it seems like none of the pieces know about what's going on here, but somehow combinations of the pieces still do. And that's kind of the hallmark of quantum error correction. Now, there's one last piece of the correspondence which I'm going to need to use for excluding global symmetries. And this is this idea of the quantum extremal surface formula. So the quantum extremal surface formula is a formula for answering the question, given a state of the boundary CFT, so here like this circle, we can compute the reduced state rho r on some boundary subregion R. Okay. And then we want to know what is the von Neumann entropy of this state on the region R. And what the quantum extremal surface formula does is it gives a bulk formula for that. So this is the bulk formula. I don't want to get in too much into the details of this, but the formula is kind of like Bekenstein-Hawking. You see there's a over 4G here of some surface, but it has a few other interesting features. So you're supposed to also add the bulk von Neumann entropy of matter fields on the time slice in between this surface XR and R. Then you're supposed to extremize that over where XR is, consistent with the fact that it's attached to R like this, and also that this space-like region is here. And then if there's more than one extremal surface, you're supposed to minimize. So this formula grew out of something called the Ryu-Takanagi formula, but it sort of grew a lot. And by the time it got to this, it sort of maybe wasn't fair to just call it the Ryu-Takanagi formula anymore. So now we call it the quantum extremal surface formula. This version was written down by Engelhard and Wall, but it probably wouldn't be fair to call it the Engelhard-Wall formula either. That would be very nice to Ryu-Takanagi. So we just call it the quantum extremal surface formula. And the only thing I want to say about this formula is that it implies something called entanglement wedge reconstruction, which is this statement that indeed, if you have an operator inside this wedge region here, which is the domain of dependence of the time slice between XR and R, so this domain of dependence is called the entanglement wedge, then any operator in that wedge can be represented in this CFTR. And in particular, this WR includes this earlier region CR I mentioned, which is called the causal wedge. So this formula implies this statement I mentioned earlier about being able to reconstruct the operators here in this CFT subregion there. Okay, this kind of redundant error correcting property of ADS-CFT. Now, I had, was there a question actually, Sebastian?
Yeah, there's a question in the chat asking, are the curves that bound CR in the bulk ADS geodesics?
Yeah, so the curves that bound CR are not in general geodesics. They are in the simple example that I drew here, but more generally they're not. However, this XR, it is almost a geodesic because well, in 2+1 dimensions. In higher dimensions, it's some codimension 2 surface. But in 2+1 dimensions, it's almost a geodesic because it extremizes the area, which here is the length, right? So that's like a geodesic, but then there's this correction here, so it's not quite a geodesic. Also, there are these ... here that I didn't say. But if you never thought about before, let's call it a geodesic. Okay. So I was going to say a bit more about that formula, but I think in particular, I was going to say that you can use it to compute the page curve. But I think I'll try to go through that. Well, let's see. Yeah, maybe let me just say from this slide that it's gradually, so this QES formula, it was understood first as computing the von Neumann entropy of a subregion of the boundary, this subregion R. But gradually now it's been understood that it's kind of a lot smarter than that. You can apply it to things other than just the piece of a holographic CFT. So that grew out of tensor networks, out of quantum error correction. We kind of showed that there's a version of the QES formula that's true in any quantum error correcting code. In particular, it was emphasized in this paper that this coding version can be applied to an arbitrary non-gravitational system, which is coupled to a holographic CFT. There's a Euclidean argument also for that. And so then somehow last year, these ideas were used to show that actually by having a reservoir coupled to a holographic CFT, you can give a derivation of the page curve for certain evaporating black holes. And so this is going to be kind of the input into the argument against global symmetries. So, okay, maybe I should continue then since we're running low on time, and then we can do more questions at the end. I have about 7 more slides. So let's go back for a sec to this Jakiv-Teitelbaum theory. So I mentioned it has black holes. Here's what the black holes look like. So the Penrose diagram is basically the same as that of the Reisner-Nordstrom black hole in 3+1 dimensions. So there are 2 asymptotic boundaries. Both go up infinity, leave into the future and the past, but you kind of don't take most of that seriously. You just say, here are the 2 actual asymptotic boundaries, and then you have this region here that's in between the Cauchy horizons, which is the actual physical region of the black hole. And so this is what the metric looks like in some Schwarzschild-like coordinates. And then this phi field, the dilaton, has a linear profile in terms of the Schwarzschild radius. You can do a Euclidean calculation of the entropy of these black holes, and you get that it's equal to the value of this dilaton at the horizon plus this phi naught parameter. So this phi naught contributes to the Euclidean calculation of the entropy. Now, in these recent papers, they pointed out that this theory has a version of the information paradox, even though it's just a 1+1 dimensional theory, which is you obtain by taking it and then coupling at one boundary to a non-gravitational reservoir system, which consists of just the same conformal matter that you had in the gravity region, but now without gravity, just propagating on half of R2. And so they showed that, so once you turn on that coupling, energy leaks out into the reservoir and the black hole evaporates. And so you can, since the theory is exactly soluble, as I mentioned, you can do canonical quantization, and you find that the entropy of the radiation obeys some curve like this, which starts out as 0, and then it grows and grows and then saturates at some asymptotic value. So this is kind of the Hawking page curve for this theory. And moreover, they showed that at least if this initial temperature is large compared to phi naught, then eventually this entropy exceeds the coarse grain entropy of the remaining black holes, at least if you believe this, this formula, which is basically the Bekenstein-Hawking formula for this black hole. And so therefore, that's a version of the information problem, right? So somehow this radiation is sort of more entropic than if it was purified by what's left, provided that we assume that whatever is left obeys the Bekenstein-Hawking formula. So in other words, the Bekenstein-Hawking formula is wrong, and that's fine. And And that's just what happens. This theory, as I said, it's a theory of remnants, like the CGHS model. And since by making T1 as large as I want, I can arrange for this entropy to be as large as I want. And so it really needs to store an infinite amount of entropy. And therefore that, and that's good from the point of view of our proposal because this theory has global symmetries. Okay. The key point, though, is that if we, instead of taking the bulk path integral seriously, like we did in the first section of the talk, we instead say this is just some low energy effectives theory, then we should instead study it using the quantum extremal surface formula. We should try to compute the entropy of the radiation using the quantum extremal surface formula instead of using just the naive low energy bulk calculation. And if we do that, then we find that there's this amazing new quantum extremal surface here sitting just inside of the horizon. In the global picture, it looks like this. So here's the Joukov-Teitelbaum region. Here's the bath where we coupled it. And now if we try to compute the von Neumann entropy of the bath system, so naively, we should just have its entanglement wedge contain this yellow diamond. But actually, you win in the quantum extremal surface formula eventually when the black hole is old enough by allowing for this island here to be there as well. And so then you get a page curve which looks like this, and you can check that this never contradicts the Bekenstein-Hawking formula. So that's kind of the the recent papers in 2 or 3 slides. Now let me just quickly get to this idea of no global symmetries. My paper with Hirose was 175 pages long. Here I'm going to do it in a slide. So the idea is actually quite simple. So say you had a global symmetry in the bulk of ADS-CFT. So you can do the contradiction either way. I'll use the left figure. So since you have a global symmetry, there must be some operator which is charged under the global symmetry. So I've indicated the operator by the green circle here. We can take the global symmetry. So if there's a global symmetry in the bulk, there's a global symmetry in the boundary. And by boundary locality, we can split the boundary up into regions. And then the symmetry operator U of G, the unitary operator on the CFT Hilbert space that implements the symmetry, I can split it up into pieces which implement the symmetry separately on each piece of the boundary. So this is basically Noether's theorem. If in the continuous case, it's Noether's theorem. It says the boundary charge is the sum of charge in region 1 plus the charge in region 2 plus the charge in region 3. And for the discrete case, you don't have charges, but you still have the statement about the unitaries. But then you get a contradiction because this green operator is not in the entanglement wedge of any of these regions. So it has to commute with any operator that just has support here or just has support here or just has support here, via this discussion we had before. But you see the symmetry operator is just made out of those pieces. And so if it commutes with all the pieces, then it commutes with the symmetry operator as well, and therefore it couldn't have been charged. And so that contradicts the idea that it was charged, and it shows that you can't have global symmetries. So to extend this argument beyond ADS-CFT, we have to make a few assumptions. So I'll introduce a system S, which is basically the quantum gravity system like the dual CFT, a system R, which is the reservoir. And then I'll just assume that I can couple them in such a way that a black hole in S radiates into R, gradually transferring the Hawking radiation. I'll then assume that I can use the quantum extremal surface formula to compute the entropy of anything, anywhere. And I'll further assume that the coupling is symmetry. So that sounded too complicated. More simply, let's just say S is a black hole and R is its Hawking radiation. Okay, let's just think about it that way. So then here's the contradiction. You just say that once the black hole is old enough that you have this island region in the entanglement wedge of the Hawking radiation, then you just run the same argument. You split the radiation up into pieces. Each of the pieces is small enough that its entanglement wedge doesn't contain the island. The full symmetry in the microscopic description, which is this system S together with this reservoir system R, the full symmetry just has to be a product of the symmetry on the quantum gravity system S together with the pieces of the reservoir. But this green dot is not in the entanglement wedge of any of the reservoir or of the system S. So the color coding here is the same as over here. I've just taken this picture and the pieces of the boundary holographic CFT, all but one of them are now pieces of the Hawking radiation. And the last piece is the remaining black hole degree, the remaining quantum gravity system degrees of freedom. And then it's just the same contradiction. So I have this charged operator here. It's not in the entanglement wedge of any of those things. So it has to commute with the same, and therefore it couldn't have been charged. So that was the argument of this paper with Edgar. I should just mention there were two other interesting recent papers that came out a few weeks after ours, which try to quantify this contradiction in an interesting way. Okay, so let me just summarize. So we've now learned a few things. So first of all, holographic theories of quantum gravity apparently work in a rather different way than low dimensional renormalizable theories of quantum gravity. And my expectation is that something like asymptotic safety would be more like the latter and not like the former. Okay. So in particular, in a holographic theory, the low energy observables are redundantly encoded into the microscopic degrees of freedom as a quantum error correcting code. And we've seen that various things that we like the Bekenstein-Hawking formula and the page curve, and the absence of global symmetries are all natural features of holographic theories, whereas they are not realized in these renormalizable theories, or I expect in anything that is like asymptotic safety. Okay, so I think that's it. Thanks for listening, and now I'm happy to discuss anything. I'm sorry for going a bit faster towards the end.
Well, thank you so much, Daniel, for the very informative talk. Let's thank Daniel. Okay, and yeah, now we have plenty of time for questions. So everyone, please raise your hands. I see Cynthia has a question. So go ahead and unmute yourself, Cynthia.
Hi there. Thanks for the nice talk, Dan. I have a question about whether we can take this as a proof that rather than an argument that there are no global symmetries in the cases you've talked about, could we take it as a proof that there's something wrong with entanglement wedge reconstruction in the case of systems that would have global symmetries?
Right. So yeah, go ahead.
Sorry, I was just going to say, because your argument relied on entanglement wedge reconstruction working correctly.
Right. So then right. So that was, so how shall I say? So I didn't, in ADS CFT, I didn't need the full details of entanglement wedge reconstruction. It was in fact enough to use this so-called causal wedge reconstruction, which can just be derived directly. So that doesn't require any fancy quantum information technology. You just solve the bulk equations of motion from the CFT, within the CFT. So that's this HKLL procedure. It's already enough to give you a contradiction. That's kind of, it's not as powerful as entanglement wedge reconstruction, but it's powerful enough to make this argument. So that's one thing I can say. The thing I can say is that there is a lot of evidence for this quantum extremal surface formula from various directions, partly from these models based on codes and tensor networks, partly from the Euclidean path integral, partly from cases where you're just able to compute on both sides and check it. And if you believe any of those arguments, then as I said here, entanglement reconstruction is a consequence of those this formula. So you would also have to say that you don't believe in either Euclidean gravity or in this error correction picture of what's going on. And I don't know, somehow, yeah, the pieces all fit together too well for me to just want to throw it all out just to preserve global symmetries, which, I mean, after all, even in the continuous case, we have this old argument by Banks and Seiberg already for it. So, my prior is not out of global symmetries.
Okay, fair enough. So you've definitely shown that there's an incompatibility between global symmetries and the QES combined with entanglement wedge reconstruction.
Yeah, or even just the QES, because entanglement wedge reconstruction is a consequence of QES. So if you want to have global symmetries, it means throw out the QES formula.
Okay.
Okay, next we have Alicia Castro. Go ahead and mute yourself.
Hi. So I have something that I didn't understand is, So if you have JT gravity and you have the black hole there, and you show us that the entropy of the radiation, I think, or of the system will be infinite if you compute it just by canonical quantization.
Yeah.
But then if you use the quantum extremal surface formula, then you get something finite. So then what's your conclusion from there?
Good. So yeah, so that kind of went into the part of the talk that I removed about Euclidean gravity. So in this theory where you just do quantum in the bulk, the resolution is that the quantum extremal surface formula is wrong. And I think that's fine because this is not a holographic theory, right? This is just a theory of the metric and the metric fields and the dilaton and bulk. And we didn't need holography. And as someone mentioned earlier, you can prove it's not holographic because the Hilbert space doesn't factorize, even though there are two asymptotic boundaries. So essentially, I would say there's just kind of two kinds of quantum gravity theories, apparently, I know. There are these funny normalizable theories in lower dimensions where the quantum extremal surface formula is not correct, the Bekenstein-Hawking formula is not correct. You can have global symmetries. And then there are these holographic theories where things are true. My guess is that, so as I said, I don't know whether something like asymptotic safety works, but if it does, I think it'll be like the low dimensional models, not like the holographic theories. So it's just kind of a choice somehow. Right. I mean, I should say that you can also, you can also still, so you could say, okay, then why did I apply the quantum extremal surface formula to JT and get a page curve that goes down, right? The reason is because even though this theory could be UV complete by itself, it might be that it nonetheless comes from a holographic, right? I mean, you can get the same IR theory from more than one UV description, right? So you should think of these two. I mean, this calculation of the entropy is really a UV sensitive calculation. So it's okay to get different answers from different UV completions. And so like if you have some Reisner-Nordstrom black hole and string theory and you go take the low energy limit, you get something like Joukhiv-Teitelbaum, but in a holographic setting, I would say. And then I would expect the quantum extremal surface calculation, because you're getting it from some UV with some meat on it, instead of just from this kind of, okay, it's normalizable, I'm not going to add anything in the UV. So it's okay, I guess, yeah, it's okay for the answers to be different in those two cases. Does that help?
Okay, yes, I see, thank you.
Sure.
Okay, next we have Deepak.
Hi, Daniel. So,
Hi.
So if I may be so bold as to try to correct the error of your ways.
Sure, please.
So your statement, first of all, that which goes back to when you said that string theory is the only theory of quantum gravity, which satisfies the properties which you mentioned, that it can be put on a computer and all that. So my main point is that, well, you also have something called loop quantum gravity. Now, in loop quantum gravity,
complete theory.
No, of course it is. It is manifestly UV complete. I mean, you have something. The state space of loop quantum gravity consists of spin networks and spin foams, and those objects.
But are you talking about what people call the continuum limit of loop quantum gravity? Talking about the theory with
No, I'm not. Right. So by UV complete, what exactly do you mean?
Well, I mean a theory where we can okay, let me give a very concrete thing. I want a Lorentz invariant S matrix at energies that are high compared to the Planck scale.
Right. So you have you can do calculations of graviton scattering in loop quantum gravity. There are some issues regarding the preservation of Lorentz invariance, but again, those questions can be resolved.
That was not my impression, and also not the impression of the experts I talked to.
Well, I don't know which experts you have talked to, because a lot of the experts, I mean, I don't know. So but the idea that you can, and another point I want to make is that, see, you mentioned a lot about tensor networks, for example. Okay, now essentially, I mean, if you agree with the work that is done in tensor networks, then you don't think that loop quantum gravity is
but I don't view tensor. I don't view tensor networks as the UV theory, complete theory of quantum gravity.
No,
right?
but if you
model.
believe the evidence coming from tensor networks to be if you believe tensor networks to be a acceptable source of insight, well, then that's in conflict with the fact, because essentially what you're doing with tensor networks is you're doing loop quantum gravity, because spin networks are tensor networks. So
yeah, I don't disagree that there is a relationship between tensor networks and loop quantum gravity, but I don't think they're the same thing, because in tensor networks, at least the ones that I like, the fundamental Hilbert space lives at the asymptotic boundary. Whereas loop quantum gravity is something like the input legs to the tensor network, but the tensor network is a map from degrees of freedom to the bulk to a boundary Hilbert space, and I haven't seen that in loop quantum gravity. I think of loop quantum gravity as being basically like lattice gauge theory, except for gravity instead of Yang-Mills fields. And there,
but it's not just lattice gauge theory, right? I mean, there is lattice gauge theory with the Hamiltonian constraint.
Yeah, but the Yang-Mills theory also has constraints, right? So it's I said it's what you would get if you tried to do lattice gauge theory for gravity. I agree it'll be different because gravity is different from Yang-Mills theory, but that's the logic. You have plaquettes, you have connections, you have a discretization of space-time.
So
and I think that's different from tensor. There is a discretization time tensor network. Step of mapping things to a boundary Hilbert space, which lives in a lower number of dimensions, and I don't see that in loop quantum gravity.
Well, I mean, okay, I'm not going to claim that I have a solid answer to all of your objections, but the idea that you can completely rule out loop quantum gravity and put string theory on a pedestal which solves all problems, I mean that is not a fair statement. So.
But did I say I can completely rule it out? So far, there's no convincing evidence for such a fixed point. That's different from saying there is such a fixed point.
Okay, all right. I mean, if you want to leave some room open, then I guess I'm happy.
Okay.
Yeah, if I may interrupt, this is getting a little bit too specialized, and I think Ro has been waiting with their hand raised for a while. So maybe let's let Ro ask their question before potentially returning to this. So Ro, go ahead.
Can you hear me?
Yep.
Yes.
Hey Daniel. So very nice talk. Thank you. I have what's probably a very silly question about your diagrams at the end, where you coupled this the holographic system to this other system, and you let it radiate out into the bath. And can you explain? Because I guess something that always confuses me in these cases, you let basically energy and radiation go from the bulk to the bath area, but what happens in the CFT? Like naively, it seems like you break the duality here, because energy seems to have to leave the CFT somehow when you couple this.
But that's because the CFT, yeah. So the CFT, maybe a different one of the pictures. This one, yeah. So the microscopic description here, if from the holographic point of view, this red dot, the CFT, okay.
Can you say that again? There was a breakup in the connection.
Sorry, this red dot here is a time slice of the boundary CFT, okay?
Uh-huh.
And then this red line is a time bath system. Okay?
Yes.
So the idea that there are terms in the Hamiltonian that explicitly couple this red dot to the red line. Energy can go both ways. It can go into the bath, it can go out of the bath.
So the CFT is now basically, when you extend the bulk, the idea is you also enlarge the CFT, so it's dual to both the ADS geometry and the flat space you tacked on there?
Well, you have to think about what we mean. The source of confusion is that there's two CFTs at work, okay? Matter CFT and the low energy bulk description, okay, which is also the CFT that's living over the side. But then there's the holographic CFT, which is dual to the bulk here. And that one actually lives in a lower number of dimensions. So here it would be +1 if is 1 plus, okay? So we have a 1 plus 1 matter CFT, we have a 0 boundary CFT, okay? The 0 plus 1 kind of like in the microscopic description, radiation, we have the +1 CFT living in the reservoir, and then the 0 plus holographic T is like a boundary condition for that somehow, but it's a boundary condition that contains its own degrees of freedom and is kind of coupled. So it can radiate stuff in and sort of absorb stuff back, right? So it's kind of, so the micro description of what's going on, if you like, is the right half of this diagram, okay? This over here, how the effective gravitational theory that emerged from the union of two.
I see. Okay. So the second system is sort of like another CFT that you couple.
But a different C, it's not holographic. It could just be free fields, right?
I see. I see. Okay, thanks.
Some people try to make it holographic literature about that, but honestly, I think it creates much more confusion than it removes. So I strongly oppose making it holographic.
Okay. Okay, great. Thanks.
Any other questions?
Maybe I can ask a question as a host. I cannot raise my own hand. So I would just like you to comment a bit more on what is your expectation of the assumptions that you make break down in other approaches to quantum gravity. So you mentioned asymptotic safety, for example. What do you expect fails in those approaches for these arguments, or why they might allow global symmetries? And I would also like you to comment on the possibility of relaxing some of the assumptions that you made. So, for example, assuming a background, or at least background boundary spacetime, for example. So, can you say something about background independence, for example?
Okay. Well, yeah. Let me make both say right. So my comments about the other approaches were not rigorous results. They were just expectations, and in large part based on these models that we had here, because my view of asymptotic safety or loop quantum gravity, which I think of as a special case of asymptotic safety, is that you're really trying to still take the quantization of the metric seriously. You want to say that the fundamental description of the theory is you have a metric and some matter fields, and somehow you quantize them. And that's what I did here in lower dimensions, right? I had some matter fields and some metric, and I quantized them. And I got global symmetry. I was able to have global symmetries. The Bekenstein-Hawking formula was not true. And so since the fundamental idea is the same, I guess I don't really see any reason why the same thing couldn't happen or wouldn't happen in asymptotic safety, assuming that it makes sense, which I don't know, it may or it may not. So that's a kind of plausibility argument, right? That's different than a proof, right? I mean, it could somehow work in a different way for some reason, but if we're really just thinking of things as matter fields coupled to gravity, then I don't see why the matter fields can't have a global symmetry. It would be that would be unprecedented in quantum field theory, basically. And I think of asymptotic safety as basically being like quantum field theory, except the metric is one of the fields. So that's the first comment. As for background independence, so let me just make let me make two comments actually. So first, even within ADS-CFT, I would say that ADS-CFT is background independent. It's not complete. The sense in which is not is just that there's an asymptotic boundary. Okay, so when we consider, all the states that we consider have certain boundary conditions that are the same. But as far as what's going on in the middle of the bulk, it's completely background independent. The Hamiltonian constraint is satisfied in all the physical states. And there are states in the Hilbert space with many different geometries in the bulk. And there's no sense in which those are perturbatively constructed around the empty ADS background. So I think for example, the Hamiltonian constraints and so on are all holding exactly in ADS-CFT. Modulo the fact that we've restricted near infinity. So the only sense in which it's background independent is that we don't know how to take the same theory and study it, say in a closed universe or, in flat space or de Sitter space, right? And essentially, I think, although this I can't prove, but to the extent that string theory makes sense, and to the extent that these different vacua are all part of theory, I think it should be background independent in the sense that it's the same theory and it allows either for de Sitter space or flat space or Minkowski or ADS. And in fact, we know examples of flat space and examples of ADS that are non-perturbatively precise in string theory. And they're certainly at least motivated by the same bulk picture of, branes and strings and so on. But they're kind of, right now in our current understanding, they kind of behave like different superselection sectors. And the best that I can say is that, in ADS, I can kind of have a region which kind of locally looks like flat space, or I can, if the cosmological constant is very small, I can compute, S matrices, which look basically like the S matrix in flat space. But I don't have like the one theory that unifies all of them, right? Like that's the sense in which we say we still don't know what string theory is, or we haven't really constructed it in the most general sense. We just there are only these super selection sectors where we've managed to understand it. But within those, there's still a limited set of diffeomorphisms, and it's fully invariant under those. I mean, all the ones that preserve the boundary conditions. I don't know, does that?
Yeah, thank you. Thank you.
Okay, I see Vicar has their hand raised.
Yes, hi. Thanks for the talk. I have two questions. My second question depends on your answer to the first question.
Okay.
So can we view in ADS-CFT, view the Hilbert space of the boundary CFT as a Hilbert space for quantum gravity?
Yes, so that's the claim here, is that there's an isomorphism between the Hilbert spaces.
Right, okay.
And moreover, as was said in the previous question, I want to say that every one of these states in the CFT Hilbert space obeys the Hamiltonian constraint.
Okay, so then my follow-up question. So the Hilbert space of the boundary CFT has global symmetries because it has global superconformal invariance, right?
Yes, definitely.
So how does that connect with the fact that there are no global symmetries?
Yeah, excellent question. Yes. So the resolution of that is that from the gravity point of view, those are actually gauge symmetries. So one simple way to think about it that I can explain already on this slide is, so say you have a U1 global symmetry in the dual CFT. So by Noether's theorem, you have a conserved current J mu in the CFT, and that operator should be the limit of some bulk field. And you can show that it's actually the limit of a gauge field, A mu, as you pull it towards the boundary. And there's a propagating photon inside. And gauge symmetries are allowed. Our theorem definitely does not exclude gauge symmetries.
So in other words, the global symmetries in the Hilbert space of superconformal field theory, the global conserved charges there are somehow from the gravity perspective gauge?
Yes, that's correct.
Okay, is there a way to see that in detail?
Well, so you can, for example, you can, so if you look at, so in conformal field theory, you can look at the 2-point function of two currents, okay? And you can compare it to the propagator of a U1 gauge field in the bulk, and you get the same thing. So that's one way to see.
I see. So I can't take the Hilbert space of the superconformal field theory in isolation and say, I've got the Hilbert space of quantum gravity, and I just have to find everything in there.
You can, but the issue is so when I say something is a global symmetry or a gauge symmetry, it depends on which duality frame I'm in. So it's the same Hilbert space either way, but the words I say are different depending on whether I want to interpret it in terms of gravity or I want to interpret it in terms of the CFT.
Okay, thanks.
Sure.
Okay. I see Jinsao Wang just raised their hand. Go ahead.
Thank you. So I want to ask, does this quantum error correction picture continue to hold beyond the semi-classical regime?
Well, let me think. So the way that quantum error correction works is that you take the full theory and then you pick a subspace of states that you like, that you call the code space.
Yeah.
And then what's going on in that code subspace are what you call the logical operators.
Yeah.
So ADS-CFT, roughly speaking, that code space is the so you can make different choices, but the simplest choice to make is that it's the set of states of sufficiently low energy,
Right.
so that there are not black holes. You can do fancier things where you include black holes, but let's first think about the case where you don't include black holes. And so then all of those states are in some sense semi-classical. I mean, they're not totally classical because you have quantum fields, right, propagating around. But they're semi-classical in the sense that nothing too crazy going on. And that's kind of the way that it all works, is because, you know, the resolution of this contradiction I had about, oh, you have this operator in the middle and how can it not, you know, commute with the operators on the edge, is that it doesn't really commute with them. But the matrix elements of the commutator are 0 in low energy states. That's kind of how it gets resolved. And then in the high energy states, what happens is, well, then you just have some huge black hole sitting here. So maybe you shouldn't have talked about that operator in the first place.
Okay. So you also have to do with black holes, I guess.
Yeah. So somehow that's why this picture with quantum error correction kind of relies on gravity, right? It's because black holes are kind of crucial to, you know, like it's, in fact, it's a theorem. So I said, how can a theory which is d-dimensional be equivalent to a theory which is d+1 dimensional? Well, so if they're both quantum field theories, the answer is it can't, right? There's a theorem that you can't, a quantum field theory knows what number of dimensions it lives in.
Yeah.
But somehow the way out is that the d+1 dimensional theory is gravitational, so it doesn't obey all the axioms of quantum field theory. And in particular, it has black holes that can kind of come in to save you if you try to really force the theory to admit that it's d+1 dimensional. You know, and somehow it can continue to be d-dimensional despite your best efforts.
Okay, then in the bulk perspective, you know, just in GR, can I understand this as sort of a feature of ADS because of the instability sort of inherently in ADS?
Well, I wouldn't. Yeah. So you mean the fact that ADS always forms black holes eventually?
Yeah, in some sense. Yeah.
Yeah, I wouldn't say that feature is essential. It's essential that the black holes exist.
Okay.
And yeah, I mean, well, to the extent that you want to view that classical instability as being indicative of the fact that at high energy, most of the states are black holes, I would say in ADS-CFT that is important. That is important for how this works. The reason why I don't want to endorse that view completely is because I think holography works in flat space too, and there you don't have that classical instability. But somehow, but you still sort of have it in the sense that if you fix a region of space and you say, what are most of the states in this region look like? Most of them are black holes, right? It's just that, you know, just the theory is not unstable because, you know, stuff can radiate out to infinity. So you never, you don't really get that instability.
Okay. Okay. Yeah.
Yeah.
Thanks.
Sure.
Okay, we're about out of time. So let's thank Daniel again for taking time to give us this talk and have a nice long discussion afterwards. Okay, and just one last announcement. Our next talk in the series will be on January 18th by Kasia Reisner. We'll have a longer break due to the holidays. So I hope to see everyone then.